This lecture focuses on sampling designs. We've mentioned through many of our lectures the idea of random assignment, random selection, and different types of samples and populations, and we're going to get into some of those details now. Our plan here is to go through and discuss sampling, particularly paying attention to random sampling and selection and random assignment. We'll cover some technology issues, some issues around sampling error and bias, and finally we'll get into some of the sampling procedures and other considerations, including some ideas around purposeful sampling. You may have heard or seen this quote that's typically attributed to Voltaire, but it's a much older proverb as well. Never let the perfect be the enemy of the good. This is true of all of our research, but more especially when we get into sampling, because we have to start with this idea of a population. In a population, it is the totality. It is all members, all elements, participants, or subjects that possess a specific set of characteristics that we're interested in, that we've defined it as. Here and throughout the videos, we'll always have our pause moments, so this is your first one. Have your research questions in mind as you go forward. I've talked a little bit earlier in some other lectures about healthy eating, and I hypothesized that those that eat healthy snacks will perform better on a mathematics assessment than those that don't. And I took that population, which could be, say, start off with all people. Then I could have narrowed down that population and said all students K through 12. I could even narrow it down further, K through 8. And then continue narrowing it down and narrowing it down. I'm still narrowing down elements of the population. We haven't even gotten into sampling yet. For my research study, in earnest, I may be interested in K through 8th graders, but for practical purposes, I may need to narrow down the population from which I would sample even further. For example, I may need to narrow it down to 7th graders in a specific state that I might want to attribute some of my outcomes toward. The reason why I think this is a good pause moment is because when we think of populations, what you want to start with is think of who is the very general population you would like to attribute your findings to. That's the very broad population. Also think of a practical population, those from whom you could actually sample. So if your population is all students in the United States, it's a very difficult population to sample from, let alone get the entire population. If you're interested in students in even a single grade, in a single state, it can be very difficult to sample from that entire population, but that still may be the population we want to target toward. So you should be thinking about both the general population you're interested in and also a practical population from which you can sample. Finally, from a population, we are going to draw samples because typically it's just impractical or we're not able to, whether it's time, cost, or just simply practical reasons, we can't actually acquire the entire population, so we acquire samples. So we start off with the idea of a population, but that is often not what we are actually going to focus on. We're going to focus on a sample. A sample is a subset of the population. It's not just narrowing down our idea of the population. It is an actual subset to which the researcher intends to generalize the results toward. Our goal with a sample is that it is representative of the entire population we're interested in. We can do random sampling or a random sample process. We'll see through random selection how we can have both a simple and complex procedure with the goal that our sample will be representative of the entire population we're interested in. And then we can also, toward the end, we'll talk a little bit about purposeful selection when we don't have random selection in our sampling process. So with sampling, really, it's because in the social sciences in particular, we only end up being able to examine a very small fraction of the population that we're actually interested in. We'll talk more about drawing inferences later on in our statistics section, which is coming up in a couple lectures. But because we want to draw inference from a sample to a population, that just means we want to connect a mathematical or statistical link from the sample we actually collect to the population that we're interested in. The selection process used to draw such a fraction is known as sampling, while the group contained in the fraction that we actually got to sample, the subset, is called the sample. So in many educational research studies, we know that it's not possible to get all of those population members. Even if we narrow it down from all K through 12 to all 7th graders, it's still no way we're really going to get all that population. So we do some method of sampling. So this is just an example of what it looks like. You can think of this circles and octagons there as a population of persons. We're going to sample from there with some sampling process, and we end up with a sample of the population. It is a subset. So it's just pictorially to give you a visualization of what we're doing through the sampling process. So we've talked a lot about randomness, random sampling, random assignment. So let's focus on random sampling. What is a random sample? Well, first, before we do that, I want to mention probability sampling. This is that every member of the population that we're interested in has a non-zero probability of being selected. So every member of the population has a chance of being selected. In our more complex sampling designs, we'll see that not everyone has an equal chance. So not everyone has the same chance, but they still have a non-zero chance. Whereas in our simple random sampling is when all of our members of the population have the same probability of being selected. A random sample is a probability sample. It's an unbiased sample where the individuals selected vary due to some random fluctuation. There's no systematic variation when we randomly sample. And we can say mathematically, statistically, we have representation of the population. It's representative of the population. So in random sampling, we have two processes here we want to distinguish between. Random selection and random assignment. They are not the same thing. We use both of these to help obtain representativeness and to eliminate bias. With random selection, we have individuals which are selected randomly, which should represent the population. They are selected randomly from the population. So to distinguish that, we have random assignment. Individuals of an intact group are assigned to different groups or treatments. So you can think of assigning the participants that you have available to you to different treatments and control. They may or may not have been originally selected randomly from a larger population to participate. So it may be that you actually have an intact group that already existed, or your group that you're going to randomly assign was from random selection. Let's take a good look graphically at what that means. Our example here, we'll start with a population. The population are smiley faces. We have blue smiley faces and yellow smiley faces. This is the population that we're interested in sampling from. So this is our population. These are all of the participants that could theoretically be in our study. And if we're doing a very simple random selection process, then we are selecting from this population and creating a sample. So those individuals in the sample, if it's a very simple random selection process, then they all had an equal chance to be selected. And there's other methodologies we'll talk about later. So from the population, we randomly select persons. Anybody could have been selected with an equal chance, non-zero chance. And because of this gives us a statistical reasoning to generalize back from the sample that we collected to the population. We say that this sample represents the population we're interested in. So let's use this just general example just to make sure we understand the logic and flow of this argument. We start with the population. This is every smiley face that we care about. You can think about it as your potential participants. We randomly select. We go through a process where everyone had an equal chance, in this case with simple random selection, where everybody had an equal chance to be selected into our sample. So this sample is representative of the population. And our argument then goes backwards. Whatever we find out about this sample, we will argue generalizes back to the population because it's been directly sampled from. So we're just taking our happy smiley faces and moving them over. So we've gone through, we've done a random selection process. And from that sample, we now have a group. That group is, we're calling it our sample. So that's a group that exists. And from that group, we might want to split it up in order to conduct some experiments. So we can do random assignment. Random assignment is going to be used where everyone has the same philosophy of randomization, but instead we're now giving them into subsamples of this sample. So now group 1 contains 2 yellow smiley faces and 2 blue smiley faces. Group 2, random assignment, has 3 of the blue smiley faces and 1 yellow smiley face. And group 3 has 2 yellow and 2 blue smiley faces. The argument now is, through a random process, everyone had an equal chance to be in any one of those groups. So the argument goes from random assignment to groups, back to the sample, and then from the sample back to the population that we were interested in and could actually sample from. Now imagine what would happen if we do not have random selection. So in this case, we have no random selection. You can think about it as having some form of intact group already. Maybe in my example, I have 7th graders from an entire school, and I'm able to do some sort of random assignment, but I cannot select those folks. Those are intact groups. So our smiley faces represent that here. So we have our yellow and blue smiley faces, but now they represent an intact group. I can still do random assignment, which gives me a statistical argument back to the group. So I've randomly assigned the treatment or control to individuals, but now the argument is not a statistical argument back from our happy smiley faces to the population of smiley faces, but it's now a logical argument. We have to say, well, these smiley faces in general represent the population of smiley faces. So the intact group we started with, we need to explain through demographics and other variables why they might represent the population we're interested in. I want to make sure our arguments are well understood. So we have gone through, we have a population that we can sample from, population we're interested in, or at least we say we're interested in. We randomly select, we've done random assignment, we've all done those nice things so we can say from our experiment where we have randomly assigned people to treatments and controls, from the population we've randomly selected, so we generalize backward to that population. But this is where you have to be cautious, and this is where I said, make sure you really understand the population you truly wish to generalize to versus the population you're able to sample from. In this case, I might really be interested in the much more general population, which in this case has red smiley faces and green smiley faces too. The argument from the population that I sampled from to the more general population also needs to be made, and that's going to be a logical argument. So just consider when I was discussing my hypothesis that healthy food will make a difference. There will be an impact of healthy food on success on a math achievement score. So those that get my apple treatment or a healthy food, healthy snack before taking an assessment will perform better than those that don't, or those that get an unhealthy snack. If, as is usual in education and social sciences, if the population that I'm interested in is all of students K through 8, and all I'm doing is sampling from 7th graders, or even more so, 7th graders from a school are my subset, I'd really need to make an argument from the population I was able to sample from to the much more general population that we're interested in. Random numbers and random number generation used to cause a lot of issues. This is just an example I'm using as a teaching tool. Nowadays, we would just use the computer to generate some random numbers. But one method was to, for random selection, is you would just have a finite population. So you'd have a finite group that you're interested in. Let's just say there's 100 individuals. From there, maybe I just want 8 of those individuals. I would start somewhere on this random table and go one direction or the other and select 8 different numbers. They're all randomly assigned, and individuals would have been already numbered 1 to 100. So now I would take the 86th, 87th, 28th person, etc. So you could do this for as many numbers and whatever sample size you wanted to do. This is just a little toy example here. Your book has one as well. You could also do this for random assignment. Let me just say a few things. One of the reasons why we don't just pull names out of a hat is because there's a distinction between random selection with replacement and random selection without replacement. If you just think about random selection without replacing the people back into the hat as a figurative example. So imagine you have 4 names in a hat and you pull one out. That person had a 25% chance of being selected. If you place that person into the group and you don't replace that person, the next 3 people have a 33% chance of being selected. So there's a difference between random selection with and without replacement. In order just to get around all of that, we either use a table. Well, people used to use random tables, but I would say in the last 20 years or so, really, technology now makes it so easy to get random selection and random assignment through using a computer. And I'll show you a simple example of that in Excel. And there's an example in your textbook with SPSS. So we'll see an example as a shorter video for in Excel, computing some of our sample selection and random selection and random assignment. But for computing our sample selection, first it's useful to have the sampling frame. You can think of this as a list of units, elements. You can think about this as a list of people's names from which the sample is going to be selected. So an example might be, you may have went to survey from a list of names of all registered voters in a district. The sampling framework, or the sampling frame here, is also sometimes just called the survey population. A sampling fraction is just the ratio of sample size to the population. So if I know, for example, I have 1,000 people on that list of names and I want to sample 200 persons, I take n, small n, which is 200, that's my sample size, over large N, 1,000, and I create a sampling fraction. So here in this case, we would want to sample 200 people out of the 1,000. You can think of that as 2 out of 10, or you can think of it as 20% or 0.2. It's also useful to note that for a simple random sample, the sampling fraction equals the probability of any member of the population being selected. So in this case, this is just simple random selection. We have 200 people that we're interested in sampling. We have 1,000 people in the survey population in the entire sampling framework. So every person has a 0.2 or 20% chance of being selected. In simple random sampling, it's relatively straightforward. We have individuals, we select a name at random. But there's 2 options really. There's sampling with replacement and sampling without replacement. Sampling with replacement means that every value is independent. Every selection is independent. So any prior selection will not affect future selections. So just think if we have a population of size 5, just to keep it really simple, and we want to select a sample size of 2. If we select a person out of sample 1 at time 1, and we replace that person, then each time we'll have the same probability of being selected. So at time 1, there's 1 in 5 people, and at time 2, there's 1 in 5 people. But it's often not practical to sample with replacement. So we can sample without replacement. One of the issues that we run into is that values can be dependent on each other because prior selection does affect future selection. So now let's just take our simple sample size, the population of size 5. We're now going to select 2. We select the first person. They had a 1 in 5 chance of being selected. They're now in our sample. The next person has a 1 in 2 chance. The dependency issue, we're not going to get into the really the weeds of it, but the dependency issue really starts to become more impactful when you have larger samples taken from small populations. You can have potential non-zero covariance issues that occur, and that's all I'll say on that for now. Just know that with our technology, the method I show you in our short little video on on random selection and random assignment, we can just sample all at once, which kind of gets us out of some of the issues of sampling without replacement for some types of sampling. Whenever we sample, we have sampling error and potential for sampling bias. Sampling error is just due to the random fluctuation when we randomly sample, and they are used to represent the population. So you've randomly sampled from the population. There's going to be a difference in that sample from the population. Doesn't mean an error has been made, doesn't mean something's incorrect. There's just going to be a difference in the values we acquire from the sample and the population. But we're going to say things like the sample, because it was randomly sampled, it represents the population well. So things aren't perfect. So for example, if you get a random sample and you get a sample mean of 99.7, we don't expect that the population mean is perfectly 99.7. It might be 100, it might be some other value. But what we're saying is that the difference between those two is just due to some fluctuation from having randomly sampled. In general, with sampling error, when we know that there's a just random fluctuation that occurs in our data based on sampling, the differences that we see, the random variances, the fluctuations due to sampling, they decrease as sample size increases. So as you get larger and larger samples, they represent the population better, more accurately. Sampling bias is a different story. It is a distortion, and it's caused by the way that a sample was selected or created so that the sample no longer represents the population that we're interested in. So for example, if we were doing our research on healthy eating and we wanted to determine if there was a difference on outcome of mathematical ability scores, if we started with a group that were already high ability 7th graders, that sample potentially has bias in it. That is, it's distorted from the general population that I might be interested in. If I'm interested in all 7th graders, or if I'm interested in K through 8th graders, kindergarten through 8th graders, I only have high ability performers, maybe on some previous assessment or previous grades. That is not the general population that I'm actually interested in. So a note of caution there on bias. Another type of bias you see all the time whenever you hear of social science research done with psychology 101 students or research methods 114 students, or whatever the research subcategory might be, done with just a subpopulation of students. And then we try to say that it really fits the general population of those that are much broader. So if we're trying to have undergraduates that are taking a Psych 101 to the population of all persons in a state, that's a difficult issue with bias, because those individuals have self-selected into courses, into universities, etc. We're going to examine several sampling designs. There are variations on the random sampling design. We're going to examine stratified random sampling, cluster sampling, and systematic sampling. We'll also mention available sampling and variations of purposeful sampling after we've gone through some of these designs. And finally, just consider some of the reasons that we might use a design that's more complicated than a random sampling process, random selection process. If we're pulling from a population that is large enough to make a random sample difficult, we want to change our design. And also, sometimes we have populations that are heterogeneous and they're very diverse and maybe have several subgroups. So we have to think about stratification, clustering, and other types of designs that get more complicated than a simple random sample. When we're determining what design we should use, there's 4 criteria our textbook goes through, and we'll just talk about them also from a practical perspective. The first is called goal orientation. This simply is the design that will best meet the goals and objectives of your study. This design will accommodate your research problem. So you should be thinking about the research questions you have, the hypotheses you may be formulating, and determine the type of sampling that you may need to do. We also have to consider measurability. Sampling design provides the data that is necessary for analysis. So if we have a statistic in mind, whether it's simple or complex, we may need to consider the sample size needed to adequately meet the assumptions of that statistic. If you have a simple statistic, you may need a smaller sample size. If you have a complex statistic that you're using to analyze your data, you may need a larger sample size. Practicality, is the design feasible for real life? So we want to make sure that we're selecting designs that are actually applicable to the real situations that are in. If you're working with school systems, you need to know that you're probably not going to be able to do some sort of simple random selection, maybe not even simple random assignment within a group. So you need to account for things like clusters and other types of environments that occur in the school system. And finally, economy is basically our limitations based on expenditures. It's our time and money. If you don't have the time and money to collect the data, then you're just never going to acquire it. So you need to make sure you develop a sampling design that meets your limitations there. And it's a balancing act. You're not necessarily going to always pick one of these over the other. If you have grant-funded research, if you're conducting research through your job, you may have more economic resources, whereas if you're a faculty member kind of going it alone, you may have very limited resources. Issues about practicality and measurability. If you know that your design, your statistical model necessary to answer your question is complex, you need to make sure you account for that when you consider the sample size that is needed to adequately determine, find the effect that you're looking for. This is just my reminder opportunity as we get into some of the more complex sampling and issues around sample size, that it's just useful for you to have your research questions, your hypotheses in mind, and you might think about how complexities of stratified random sampling or clustering sample might impact your study and research. Stratified random sampling is really similar to random sampling, or simple random sampling. Now we have, instead of a homogeneous population, we have a heterogeneous population. That just means we have several subpopulations within our total population. We can divide the population into two or more subpopulations called strata, and the researcher defines what these strata are, what are meaningful in your research. So all strata should be represented in the sample. Random selection is included by selection within the strata. So now we divide up our population into our subpopulations, and within each one of those strata, each one of those subpopulations, we're going to do some form of random sampling. And then, of course, this ensures that no subpopulation will be omitted or overlooked from our sample. When considering some more of the reasons why this is important, is we want to guard against any sort of wild sample that could occur, something that would be just in the fringe of our populations. It ensures no subpopulation is omitted from the sample, and it also avoids overloading of a certain subpopulation. So when it comes to stratification, the strata should be meaningful to your research. It could be education level, ethnicity, income, gender, geographic location, whatever it may be in your research where you think that there's no longer homogeneous population and the subpopulation needs to be accounted for. So for example, using our smiley faces, we have different colored smiley faces here. We might want to break those up into different strata, red, orange, yellow, green, and blue. And now we can randomly sample within each one of those strata, which will ensure that we have members of every level of the strata in our final sample. So we formed our strata. There's two different methods of allocation of sample size among our strata. The first is equal allocation. We just take the equal number for each strata. So in this case, if we had 10 in our sample, we would just take 2 from each strata, regardless of the original strata size. Another method would be proportionate. So for each stratum, we contribute to the sample a number that's proportional to the original population. So we can see here that red has 2, orange has 1, yellow and blue both have 3, and green has 2 as well. You should be thinking about your sample size in a smaller sample. You want to make sure that you accommodate each strata. So here I added actually the sample size from 10 to 11, just to make sure there was a more balance amongst the strata. We sometimes call our stratified random samples self-weighting samples, and depending on which of the methods you use will determine the probability that somebody's actually selected, both from within a strata but across strata as well. So proportional allocation is much more frequently used. Sometimes people will use equal allocation. It will depend on the statistical model they might want to run afterward. They may choose that, but most frequently we see proportional allocation. And you can have multiple strata. You can pick more than one variable. You could have socioeconomic status of individuals plus geographic location, or you can pick multiple strata, but it gets complex. It can get complex with lots of strata quickly. And the larger the sample, the more strata one could have in a design. But you often want to be careful not to pick too many stratum, that you're getting to the point where you have 20, 30 different stratum that you're dealing with. Another procedure we sometimes use in sampling is called cluster sampling. The unit of selection, which we call a cluster, it contains two or more members of a population. Each member of that population is uniquely contained in one cluster. So random selection occurs with clusters, not individual members. All population members of that selected cluster would be included in the sample. There's some advantages here. There's reasons we might do this. The selection of an individual member of the population may be very expensive or impractical or difficult to collect data on. And you are working with really large populations, you may want to do some form of clustering. In order to think about cluster sampling, you just got to think about clusters. So instead of randomly selecting an individual person, we're going to randomly select a cluster. It could be classes like at our university or in a high school. It could be different cohorts that we're selecting, different years of graduation, or city blocks. I once did some research with organizations doing some cluster sampling in DC, so they would select different districts. Each district would have a random chance of being selected, and you would select the cluster, and then people would walk the entire area and sample from that entire cluster. So the exact size of clustering for a cluster sample may not be known until after the sample is actually selected. You may not know once you randomly selected equally amongst all of the clusters, all of the city blocks, or all of the districts in DC, you would have potentially different sample size after the clusters were selected. And sometimes individuals do both cluster and stratification. So these are not mutually exclusive. You can do clustering and then still stratify your sample. So the sampling at the unit level could be simple random selection, but it could also be stratified stratified selection as well. So many of these designs can be pulled together to make a much more complex design. Just our recap, our simple random sampling we've been through so far this lecture. Every person in the population of interest can be selected. We think of a name out of the hat. It could be with or without replacement, but everyone's got that chance of being a non-zero chance of being selected. And we just saw the difference between with and without replacement. But often it's the case that we have a list or some way of acquiring names that we can do systematic sampling. So what we can start by doing is randomly select the first member of the sample. And then from that point forward, we can take every kth person from the list. So our sampling fraction is 1 over k. So you can think of, if I want to have 1/3 of the people from the population in my sample, then our sampling fraction is 1 over 3. And we're going to sample every third person from the list, starting with a random point from within the first 3 people. So here, the simple example is we start with the second person, go to the 5th person, go to the 8th, and go to the 11th, and we would continue on periodically. So you'll also notice that the major problem with this could be an issue with a periodic function. Periodicity is the issue here. So if for some reason people were being selected in, every other or every third person had a similar characteristic, on our list, then we could have a potential violation here, a threat to validity. So, but in general, systematic sampling is a common practice, but maybe an unnecessary one in today's age with computer technology and our ability to do random selection and random assignment with things as simple as Excel or our statistical software packages. A very common question that I get is, how large of a sample size do I need for my research? And there's a lot of factors that go into this. You know, the sample size that you need really just depends. It depends partially on the results of an analysis. We want the results of our analysis to be accurate and precise. And we can do some sort of sample size determination. This is an analysis which depends on the statistical method that you're going to use. And we can determine ahead of time, a priori, what sample size I need to find an effect that I believe exists. So the first thing I'll say, though, is money and time should be estimated. So it's not just how many dollars you have, but what are the practical implications in collecting data for your study? How much time, how much effort goes into that? And you should estimate the cost of obtaining each individual in your sample. Each person, each unit in your sample is associated with a cost, and that should be estimated to the best of your ability. And then in order to determine sample size, we need to know some things about your research. We're going to be, in a couple weeks, talking about some of our statistical methods, but just as sort of a foreshadowing, we're going to select a statistical method, and that statistical method, we're going to have to know things about how precise our statistical precision. We're going to want to know about statistical power, effect size, and alpha. You can just think for now of alpha as chance of making an error. When I know these elements for determining sample size, when I know the precision, the power, the effect size, and alpha that I'm setting, then I'm able to determine my sample size. It's just a reminder that as we get into some issues around sample size, that it might be useful to have your research questions and your research's ideas at hand. Think about what might be implications for your research and your hypotheses. It's going to be helpful to define some of these terms. We're not going to define them mathematically yet. We're going to talk a little bit more about things like standard deviations and standard errors later on in our statistical section of the course. But for now, it's useful to define this in words. Statistical precision is the closeness with which it can be expected to approximate the relevant population value. It is necessarily an estimated value in practice, since the population value is generally unknown. So we can think of it's an estimate directly related to our sample size, and it's related to the ideas of confidence intervals and margins of error. This precision is usually estimated using a standard error in statistics. The larger the sample, the greater statistical precision we have. You can think about precision as how close together are our values. When we think of precision, it's how closely related scores are. When we think of accuracy, we think of how close the values that we get, or the average value we get from our sample, is related to the population. We often hear about this in election time. So just imagine you hear someone has a 48% chance of winning, and they say they have a margin of error plus or minus 3%. They may give out like a confidence interval of 99%, right? So just focus on the fact that the person has a 48% chance of winning. So we've sampled a group. That distribution represents their sample. So we say that the score that is most likely, the score that we have is a 48% chance. But with that margin of error of plus or minus 3%, the real value could be anywhere between this 45 and 51% chance of winning. That is just based on the sample. The truth of the value we don't know. We didn't take a census of the entire population. The true value could be more like something like 40%. So precision is how closely the scores are nested within each other, and the more precise we are, the closer those values are going to be to each other. We're going to come back to this idea again. This is actually just your first time encountering ideas about precision, standard deviations, and standard errors. We're going to come back to those ideas when we get into our lectures on statistics. The next term we're going to define is statistical power. This is whether a result is statistically significant. Did we find a difference using our statistic? We hear things that are said like the probability that a specific statistical test will reject the null hypothesis when the null hypothesis is indeed false. Well, that's a way of saying that we have a chance of rejecting the fact that there is no difference when we should. So in our experiments, in our research, if we have a treatment and control, if there's no difference between those two groups, then we didn't find any effect. And that is what the null hypothesis is related to. We're going to talk more about null hypothesis testing later on. It's just useful to bring it up in terminology now before we get into our statistical lectures in detail. Another way of thinking about statistical power is our ability to detect a difference if it exists. It's the probability that if there is a difference that we can detect it. And with larger the sample size, the greater the statistical power. Again, these are just preliminary definitions. There's nothing mathematical that we're putting up here right now. These are just the definitions in language so that we get intuitions around these ideas that when we talk about power, we mean it's our power to detect a difference should it exist. We also want to define what an effect size is. First, let's situate ourselves. We have a statistical test to determine if a treatment and control group differ. And we mean that statistically. So is there a statistical difference which we can say represents what should be in the population? So if there is a difference, then the two groups, the treatment and control, or three groups if we have multiple treatments, then the groups are not equal. If there is no difference, we could say there is no effect. If there is a difference, we could even estimate it ahead of time with an educated guess and determine what that effect should be. So in my example, I use as a running example in a lot of the lectures is my hypothesis that healthy eating will have an impact on a mathematical assessment. You can think of any assessment. So our healthy eating will, if you eat a healthy snack before taking an assessment, that will improve performance than if you didn't eat one or you ate an unhealthy snack. So if there's a difference, if we're going to try to say that there's a difference, that difference is the effect. Often we like to say things like there's small, medium, or large effects. We like to try and give quantitative values, some sort of qualitative measure here. But we can estimate these effects. We can give values, mathematical values in practice to these effects. But you can think about them, an effect size in general, as being a small effect, a medium effect, or a large effect. A small effect means there's a small difference between the treatment and control group. A medium effect means there's a medium difference, and a large effect that should be kind of obvious. So in a sort of a lay term, when I think about small, medium, and large effects, I think of large effects as anybody should be able to see those differences. Medium effects it usually takes an expert to detect those differences without a statistical test. And a small effect, really we are relying on statistical tests to be able to see the differences between our treatments and controls, if they actually should exist. The effect size is the difference between some critical value, that effect that we're predicting, and the specified value in a null hypothesis. The null hypothesis basically states there's no difference, that there's no difference between our treatment and control. We'll come back to these ideas again when we get into our descriptive and inferential statistical lessons. As a short recap, our precision is how closely values are related to each other. Our power is our chance to find a result, a significant result, a difference between our treatment and control should it exist. The effect size is the magnitude, the size of the difference between our treatment and control. And we'll talk more about alpha later on, but that's our chance that we could always be making a mistake. What you might want to do is start thinking about your hypothesis and consider issues of effect size. What is the magnitude, the size of an effect that you think might really be there? If you're looking at a difference between a treatment and control, is it going to be a small difference or a large difference? How could you change that difference? What's the power you think that you'll have? What's the chance you can find a significant result if it really should exist? So these are some chances for you just preliminary to start thinking through some of these ideas and how the implications it might have for your own research. We're going to do this again in our lectures later on in statistics for descriptive statistics and inferential statistics. But it's useful to start thinking about these ideas now. Very briefly going to touch on some of the purposeful sampling. We often use purposeful sampling more in our qualitative studies. It's used when a researcher selects a sample to meet the purpose of the research, and it's not at random. So the researcher must be very knowledgeable about the characteristics of the units or persons they're interested in, such as the variability that exists and the existence of extreme cases. Comprehensive samples includes everyone with a specific characteristic. Typically, because this is a qualitative endeavor, you see small sample sizes. You can think of a historian doing biographies or an analysis of a single event. Maximum variance sampling is we provide the greatest difference in certain characteristics. So we may have two types of information that are generated. We want to know the detailed descriptions of the cases that highlight their differences. And also we want to know the commonality across the cases in spite of their variations. We may also do some purposeful sampling based on extreme or typical cases. Extreme cases are there's a unusual characteristic or a special characteristic about some individuals or a group. Perhaps there's a school that has a new methodology that they're using and it has been very successful. So we might take a deep dive into a more extreme case, but we could also do sampling of a middle of the road case. So maybe there's just an average school in a state that we want to explore and see what typical phenomena there are when we explore a typical case. There are some other versions of purposeful sampling. If you're interested in just focusing on a specific subgroup, a particular subgroup, that could be a homogeneous sampling network or snowball samplings when you have individuals you have selected, and those individuals suggest other people's names that might be appropriate for your sampling. In certain situations in research, it's very difficult to find people with certain characteristics, so we might consider snowball sampling. There's intermittent selection, where you are selected for the sample as the research is already in progress. And finally, internal sampling, which is you identify samples and documents to be reviewed and subjects to be observed. There are, of course, advantages and disadvantages if you were to use purposeful sampling. I mean, the possibility is that you can generalize through a theoretical or logical method from your sample to the general population, but be cautious, don't count on that. In a qualitative research study, it may be different stages of the study. There may be multiple stages, and different stages may need different techniques. But be very careful, especially in quantitative research. This method, purposeful sampling, are highly prone to research bias because with purposeful sampling, it involves the judgment of the researcher, and it is not a good defense when comparing probability sampling compared to our probability sampling techniques. It's difficult to defend that your sample is representative, and those that are evaluating, reading, or if you're peer-reviewed articles, it's difficult or impossible to justify purposeful sampling when you are dealing with some of the statistical techniques that we will consider. It's often acceptable in qualitative research, though. So we want to make sure that the readers are convinced, whatever sampling technique we may use, that we had justification to generalize to a larger population. And with purposeful sampling, because of the judgment and the value-latedness and the bias that could be potentially there, these are not typically useful techniques for quantitative research. Just as a reminder from earlier on, the issue with sampling, whichever method that we're using, the issue is about the argument. It's about the argument that the sample that we have is representative of the population. We believe that through some form of random selection, whether it's simple random sampling, whether it's systematic sampling, stratified random sampling, clustered sampling, or combinations of them, that arrow from the population to the sample is justified. And we believe that that sample represents the population. True of random assignment as well, that we believe when we do random assignment that each one of those sub-samples that we have that are going to be assigned to treatments and controls, that they represent the sample that we have. So we want to be able to go backwards from random assignment through our sample to the population. When we have random methods, when we have simple random sampling or stratified or clustered sampling, we have justification mathematically and statistically back to the population. Anytime we do any purposeful sampling, we break that bond between the population and the sample, and then we have to argue it logically. The best of all worlds is that you have a random method that you've done for selection purposes, and afterwards you review your demographics and can also make a logical statement about it. So in general, we would really like to have maintain random selection as much as we can, but we know in practice that in education and other social sciences that we end up with an intact group instead of a random selection. And summing up, I want to say a few other things. That often we have a multi-stage sampling which involves multiple methods. We can have sampling which involves clustering and systematic sampling or a stratified random sample. So we want to be sure to document well whatever sampling procedure we're using, whether we're using simple random selection and random assignment, whether we have a complex methodology. We want to make sure to document that. We want to be able to document the demographics that we use, and all of this will aid in the generalizability of our sample to the population. Just as a reminder, this is really a light introduction to sampling techniques and some of the procedures on sample size determination. If you get more interested usually in our statistical courses, there's a lot of information on sample size determination, but there are really degrees and courses that focus on sampling design. So if you get more interested, there's a lot more out there for you. Our next lecture is going to be covering issues around measurement and some data collection. So if you're interested in reading ahead, you can read through our chapters on those topics.